Hello everybody, welcome to Lesson 4.4, Translations and the Quadratic Family. You're expected to take notes on today's video as I provided you with a notes guide on the wiki that you can print out. A few of you picked them up before you left class today after the quiz. If you can't print it out or you didn't pick one up, go ahead and just take notes in your notebook. I am going to be coming around tomorrow at the beginning of class just to check to make sure that you did watch the video and that you did take some notes on it. I am going to check up on you a little bit tomorrow. So let's go ahead and talk about translations in the quadratic family. We're going to recap what these basic transformations are, talk a little bit about places you might see translations in math class and elsewhere, and then we'll talk specifically about the parent function y equals x squared and the parts of a parabola. On this slide, we have a couple of places where we might see translations in other settings. We're focusing on Algebra 2, where you might see it, but you could also see translations in statistics and even in geometry as well. So let's go ahead and take a look at this histogram that you see here. It's on the test scores of students in a class and the number of students that scored within each range. You can see that we had about 2 students in this example scoring between 50 and 55, whereas between 70 and 75, 4 students scored in that category. Well, let's imagine that the teacher was a nice guy, and decided to give everybody 5 bonus points on this quiz. Well, the whole graph then would translate because of those 5 bonus points. If every student had 5 extra points, then this entire graph, this entire histogram would slide up 5 units along the x-axis. So the graph would translate right 5 units and look like the red histogram that you see there. That's an example of a translation in statistics. In geometry, I think you did this a little bit last year, and maybe in middle school as well. You see this gray-colored or purple-colored triangle. You can slide it. I think it was called an image. You can produce the image of this triangle by sliding it. Looks like this guy goes right 5 and up 1 to produce the image of that triangle. In music, we can see an example of a translation. I thought of this example, the concept of an octave. If you are familiar with music, they might say, oh, let's take that up an octave or down an octave. Here we have the music to Twinkle Twinkle Little Star, and you can see that every single note has been translated either up or down, either up or down an octave. So that would be a translation of all those notes up or down. Let's see, what do we have next? We have an example of translation in art. I immediately thought of Escher. I used to have tons of Escher pictures around my classroom, and I realized they became too distracting for the students, so I took a lot of them down. But here would be an example of an Escher painting that would have translations. I remember I had this one in my room, taking a minute to load. But think of these fish and the birds and the fish here as being translated to the right. It's basically just the same exact shape that's moving around on the screen. So that would be a translation in art. And finally, architecture. I thought about, this note here. It said other examples, music, art, and architecture. I immediately thought of this place in Pittsburgh where lots of people go to get their pictures taken when they get married. It's called the Mellon Institute of Industrial Research. It's part of Carnegie Mellon. And here's the building. It's actually impressive here. It says its signature monolithic limestone columns are the largest monolithic columns in the world. A little bit of Pittsburgh trivia there for you. Here's the actual photo. And you think of it as a translation because it's basically the same exact column that is replicated going down the building from left to right. So that would be an example of a translation in architecture. All right, so translations are everywhere. Let's move on and let's talk specifically about translations in algebra. Well, translations aren't the only type of transformation that we talked about. The change in blank or blank of a figure or a graph is called the generic term is transformation. Transformation. Transformation is the change in the figure's size or its position. It is not the change in the shape. The shape, the general shape holds true, but you change its size or its position. I have them color-coded here for you. A dilation is the one that would control the figure's size. For example, this star that you have here, if I made it larger or smaller, that would be called a dilation. We talked a little bit about that last week. That's the blue dilation. The change in the position would be either a reflection or a translation. This is a brief recap of what we did last week. This would be a reflection of this big check mark. If you flipped it to the left or if you flipped it downward. That's called a reflection. All right, let's get that out of the way. And the one that we focused on with lines, it was called Lines in Motion, was the name of the last section. That would be the translation that we're going to be talking about. This could be the line y equals 2x. Just on this recent quiz, we did things like slide this line up, slide the line down, slide the line right, or slide it right, left, up, down, all those different ways that we would slide the line. If we took this line and slid it up 2 units, then the new equation would be y equals 2x plus 2. We did many other things with it. With sliding it down 8, you would make it 2x minus 8. And then we also talked about what controls its left and right movement, which we'll talk about a little bit later in the next lesson. But today we're going to move on from just working with these lines to a new type of graph. And that graph is going to be the parabola. Okay? So in this section, we will work with translations of a graph of the function y equals x squared. The term for the function y equals x squared is a quadratic. That's what it is called. Quadratic. That is the name of the function. The name of the graph that it produces, this guy that we see here, is a parabola. Just like in the last section, a line is what's produced. A linear function is what produces it. A parabola is what's produced. A quadratic function is what produces it. Now, the parabola has many parts to it. The line doesn't have too many. It just has the slope and the y-intercept. But the parabola is much more extensive. It has one thing called a line of symmetry. Let's talk about that. The line of symmetry is a vertical line that cuts your parabola in half vertically. So in this basic parabola, this would be the line of symmetry. We indicate it with a dotted line. The line of symmetry would be the line x equals 0. The line x equals 0 is the line that cuts this parabola that you see here. Okay, this is the parabola I'm speaking of. That's the line of symmetry that cuts it right in half. Now, along that line of symmetry is an important point known as the vertex. So let's talk about the vertex next. The vertex is the lowest point on the graph, or the highest point on the graph. In this case, the vertex would be this bottom point, 0, 0. Now, since it is the bottommost point on this graph, it's known as a minimum. It's a minimum when it's the low point. If this parabola was flipped the other way, like this, if this parabola was upside down, then that vertex would be known as a maximum. It's a maximum when it's a high point. Right there would be the maximum. It is a minimum when it is the low point on the graph. So the vertex can come in 2 forms. It can either be the maximum or the minimum. Again, maximum if it's the highest point, minimum if it's the lowest point. All right, other parts of the parabola that are sort of important. We have the y-intercept and the x-intercepts. And basically, those are kind of easy. The y-intercept is the point at which it strikes the y-axis. We'll call it 0, c. It's where it hits the y-axis. And the x-intercept, or intercepts, you can see there that I have it sometimes plural. You might have one x-intercept. You might have two x-intercepts. You might actually have no x-intercepts. Let's explore that here. Now, I know that y-intercept and x-intercept aren't really on your paper anywhere. So you can go ahead and just take additional notes in the margin or on the back if you'd like. But the x-intercepts can look like this. If we think about the ways that a parabola could happen, here are three examples. Here's a parabola that opens upward and hits the x-axis twice. So this is a parabola that would have 1, 2 x-intercepts. Okay, 2 x-intercepts. That's that case. But it's also true that a parabola could sort of come down and just hit the axis, sort of like this. And then it just strikes and then bounces back up, and it only hits that x-axis one time. So this is a parabola that would have 1 x-intercept. All right? Finally, let's imagine that parabola up a little bit higher even. Let's use the black spray paint here. If this parabola was drawn up higher, how many times would it hit this x-axis? 0. So this is a parabola that would have 0 x-intercepts. All right? So be aware that all three of those conditions are possible. Now, whether these parabolas are right side up or upside down, all three of these are possibilities. 2 x-intercepts, 1 x-intercept, and no x-intercepts. Next, let's talk a little bit about this concept of a building block function. Now, I know it as more of what's called a parent function. Those are synonyms, just two different ways of expressing the same thing. A building block or a parent function is the most basic form of a function without any changes or transformations being applied to it. So we talked about the line y equals x in class. And that line would just be the basic line that starts at the origin and goes up and to the right and then down and to the left. That's the line y equals x in its most basic form. It hasn't been shifted. If you added 2 to it, you would take that line and slide it up 2. Okay, let's pretend that that's 2 units. 1, 2. If you took that line and slid it down 5 from its original position, then it would land down 5. So the function has been changed. It's no longer its parent function, but it's sort of like an offspring, y equals x minus 5. Parent function is just in its most basic form. What does this function look like? Well, the y equals x squared parent function looks like this. I want you to be familiar with these key points that are on the equation, or the graph of y equals x squared. Y equals x squared. We can think about these points in terms of a table of values. What happens when we plug in 0 and square it? We get 0. So let's plot that point, 0, 0. What happens when we take 1 and square it? That means 1 times 1, which is 1. So you would go over 1, up 1, and put a dot. Now let's take 2 and square it. You get 4. Over 2, up 4. This is why the parabola has this curved nature, because as you're squaring it, it starts to get steeper, because you're multiplying each input times itself. Now let's think about what happens as we go to the negative side. Negative 1 squared. Well, if you do this properly, negative 1 squared means negative 1 times negative 1. Well, negative 1 times negative 1 is positive 1. So you go over to negative 1 and up to positive 1. So you can see how the parabola is coming down, hits its minimum, and then starts to bend back up. If we made the 2 negative, the output, y, would be positive 4. So you go left 2, up 4, left 2, up 4, and you notice that as you're going to the right, the mirror image is happening to the left. So that's why we call the graph symmetrical. And that's why we call the line that cuts it in half its line of symmetry. Okay? So those are sort of the basics of the parent function y equals x squared, with key points 0, 0, 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4. Those are the key points on the parent function y equals x squared. Now tomorrow we're going to start this investigation. I'm happy that you were able to watch the video tonight so that we'll be able to hit the ground running and talk about this investigation together. We can spend a little bit of time at the beginning of class going over any of the basics that you didn't understand or that I perhaps went too fast on. So feel free to ask questions and get involved. All right, see you tomorrow. Thanks.